All right, so we talked about friction. We also talked about friction in wedges as an application of what we learned generally about the theory of friction. Now we want to talk about friction in screws, another application of theory of friction, I would say. And this application is more geared towards, I would say, engineering design. When you design a machine or a system, you're going to end up designing uh, multiple, or at least few, typically screws or fasteners or connections or connectors. So in this case, we're just going to look at the screw and see how can we use what we learned from theory of friction to analyze the screw and the way the screw moves, or better to say the screw's motion, and find the relationship between the friction and the force or torque applied to the screw. Right? Now, screws typically are used for two purposes, right? Typically, these two are the main purposes for screws. We either use them to connect two or more pieces together, more like a fastener or connector. You want to think about it that way, or we use them to transmit power or motion. Right? So let me write it this way. So screws are typically used as fasteners to connect two or more pieces together, or we can also use them to transmit power, right? To transmit power. Now, the first case is probably the most typical application of the screws you have seen. I brought a couple of figures here. The most simplest situation would be you have a screw, you have a set of, let's say, nut and bolt, and you are trying to connect two pieces together. Now, those two pieces could be pieces of a bridge, or could be some small pieces in some small, I would say, electronic device that you're trying to connect together. So that's where screws are used as fasteners. But when we talk about transmitting power, the best example that is probably the most common example I would say you see in daily life is a car jack. Now, when you are trying to, or when you use a car jack to lift up your car, what you are doing basically is you're applying a torque or a moment to the screw, right? You're trying to turn the screw, and this screw, as a result, transmit this motion, this torque, this moment you're applying, this power uh, as an input you're applying to the system into a different type of motion, right? It transmits this motion or power into vertical direction, let's say, when you are trying to lift up your car. These are two typical applications for screws. Now, later on, you'll see in a course, in some courses, in other courses like solid mechanics or machine design, I think in solid mechanics, better to say, you start looking into how to calculate the strength for screws under different loadings and how to find out how strong the screw should be, or your nut and bolt should be, to be able to handle the loading of your structure. And later on in machine design, you'll learn how to actually pick the correct screws for specific applications when you're designing something. But that's not the purpose of the topic, at least in this course. In this course, we'll look at just the relationship between moment and the force you apply to the screw, and how does the friction between the screw and the bolt, or the part that the screw is passing through, how does that friction relate to the force you're applying, and how can we use our knowledge of friction and drawing free body diagram to find this relationship, right? Now, if you think of a screw as actually a wedge, right? That's how we can actually think of that. Now, start with a screw, right? The general form of a screw with multiple threads on it. And if you unravel the entire thread, let's say one thread going from A, right, goes and you go around, come from this side and then go around to this part, right? And here is the simplified version of that. You're just looking at one thread. Now, if you unravel that thread, what happens is that you're going to end up getting a wedge-like kind of piece. All right. I basically, this picture is the unraveled version of one thread. Or is the radius for the screw. So that means the length of this side, this length, I don't want to make it crowded here. This length, this side here is going to be 2 pi r, right? You have a circle, you unravel that, that length would be the circumference of your circle. So it's going to be 2 pi r. And then you have L here representing this height. Now, this is known as lead, right? Basically, lead of a screw is the distance the screw advances in one turn. So when you turn the screw once, how much that the screw moves up or moves down, or better to say advances, because it can be in any direction. In this case, how much it goes up or down. That L is called lead. Right. Theta here, I'm just going over some terminology. So this is a lead. This is called lead. Theta here, looking at the geometry, let me just use the terminology first. They call it lead angle. And based on the geometry, you can easily say theta is tan inverse L over 2 pi r. L being the lead for the screw, r being the radius of the screw. And that's just the general, a little bit of terminology and how can we look at this. Now, when we have this screw inside, let's say a piece of material or a part in a system, or we have a bolt around it, there is going to be two surfaces, right, in touch with each other, right? You have the thread from the screw and then you have the surface from the bolt. Now, depending on this lead angle, the lead, and the moment you apply it to the screw, you can have 4 possible cases. Remember when we were looking at friction, we said for a part or object under friction, the object can either be static, can be in impending motion state, or it can be in motion, depending on the relationship between force and the friction in that particular case that we're looking at. Now here we're going to have 4 possible cases or 4 possible outcomes, which depends on, again, friction, the moment we apply to this screw, and the radius, typically the radius of this screw, right? So next we're going to look at those 4 possible outcomes or cases and see how do we deal with this screw and bolt or screw when it's inside a part. How do we deal with that, and how do we find the relationships that we need so we can use that for design purposes?